Alright, ladies and gentlemen, welcome to the third and final video for the 5-3A notes over solving linear equations. So we got three examples to go in the notes. We're just going to knock those out real quick. These are the most tricky of the equations we've had to solve because the method that we're going to use to solve these problems can actually create extraneous solutions, which means that when we get done and we have our answers, we have to check those answers. So here in the first example, we've got cosecant minus cotangent is equal to 1. In order to solve this equation, we need to move the cotangent to the other side of the equation. What that gives us is the cosecant of x is equal to 1 plus the cotangent of x. Now, we cannot substitute directly into this based on what we have to get down to just one trig function. But if we square both sides, then we would have the ability to get rid of cosecant using our Pythagorean identity. So our next step and our approach overall in this type of problem is we are going to square both sides. Now when we square both sides, on the left side we have the cosecant squared of x, but on the right side, remember that when we square a binomial like 1 plus cotangent of x, we're really multiplying it by itself, which means we need to FOIL it, which means we would be looking at 1 plus 2 cotangent of x plus cotangent squared of x. So that's just some side work. That means our equation becomes 1 plus 2 cotangent of x plus cotangent squared x. Now again, the reason that we did this was because now the left side of our equation, cosecant squared of x, can be replaced with 1 plus cotangent squared of x. So we do that, which gives us an equation that only contains cotangent of x. And that allows us to solve that equation for cotangent of x. Now this looks like a quadratic equation, but when we start moving stuff to solve it, and we move the cotangent squared, it actually cancels on both sides, which means in reality what we need to do is move the number away from cotangent. Now that's still tricky in this particular example because when we move the 1, we get a 0. So we have 0 equals 2 times the cotangent of x, and then we divide by 2 to get the cotangent of x is equal to 0. So that means we are looking for values of x, angles, that have a cotangent of 0. Now remember, we said this before, since cotangent of x is equal to cosine of x divided by sine of x, the only way that the cotangent is equal to 0 is if the cosine is equal to 0. So we are looking for angles where cotangent is equal to x, which is really angles where the cosine is equal to x. So we go to our unit circle, and on our unit circle we are looking for any x value of 0. That happens here at pi over 2 and here at 3 pi over 2. So that gives us two possible answers for x. X is either pi over 2 radians or 3 pi over 2 radians. Now, the downside is that this process where we squared both sides, right here, this step creates the possibility that those answers do not in fact exist. So we have to check our answers. So let's start by checking x equals pi over 2. We plug that into the original equation, the cosecant of pi over 2 minus the cotangent of pi over 2, and we're checking to see if that is equal to 1. Well, the cosecant of pi over 2 is 1 over the sine of pi over 2. The sine of pi over 2 is 1. So that says 1 minus, we've already said the cotangent pi over 2 is 0. Does that equal 1? Yes, it does. That confirms that pi over 2 is a solution. However, when we check the other possible solution, 3 pi over 2, the cosecant of 3 pi over 2 minus the cotangent of 3 pi over 2, does that equal 1? The cosecant of 3 pi over 2 is 1 over the sine of 3 pi over 2. The sine of 3 pi over 2 is negative 1. So that says negative 1 minus 0, and that does not equal 1, meaning that 3 pi over 2 is not a solution, and it gets thrown out. The only answer to that particular question would be the angle pi over 2 radians. 2 examples to go. They're on the same slide. Both of these are going to use that same basic approach. So, on the first one, it's already separated with one trig equation on, or one trig function on each side, so we're going to square both sides. Remember that the second that you square both sides of this equation, you create the possibility of extraneous solutions, because when you square a negative, you make it a positive, which means that you could screw up and end up with a false answer. So we have to check our answers. Again, when we multiply secant x times itself, we are going to get secant squared plus 2 secant plus 1, because we have to FOIL secant x plus 1 times itself. On the other side, we have tangent squared x. Now, tangent squared of x can be rewritten as secant squared x minus 1, one of the versions of your trig function, or trig identity. On the other side, we still have secant squared plus 2 secant x plus 1. So when we go to solve this equation, just like on the last example, we go to move the secant squared to the same side, and it cancels out. So that means instead we need to move the number away from secant x, giving us 2 times the secant of x equals negative 2. Divide by 2, and we get the secant of x is equal to negative 1. The secant is equal to negative 1 wherever the cosine is equal to negative 1. So we are going to go to our unit circle and look for a cosine value of negative 1. The cosine is the x-coordinate. The only place where x is equal to negative 1 on the unit circle is pi radians. So that is the only possible answer here, is negative 1. Okay, so, secant of x equals negative 1 means that x could only be pi. Okay, there's no other place where the cosine is equal to negative 1. So then we need to check. So we check x equals pi by plugging it into the original equation. The secant of pi plus 1, does that equal the tangent of pi? Well, the secant of pi is equal to 1 over the cosine of pi, which is negative 1, plus 1. And the tangent of pi is the sine of pi, 0, divided by the cosine of pi, negative 1, which would be 0. So this does work, and that is the correct solution. On to the second example. Okay, again, it's already set up. We square both sides. That gives us cosine squared of x equals sine squared of x minus 2 sine x plus 1. Then we replace cosine squared with 1 minus sine squared x using a Pythagorean identity. Now this one is a little bit unique compared to the other one, because this time sine squared does not cancel. So when we move the sine squared, we move it to the right side so that it is positive. And while we're at it, we're going to move that 1 as well so that we get one side equal to 0. So 0 is equal to 2 sine squared x minus 2 sine x. Technically plus 0, we don't need to write the plus 0. This is a factoring problem. There's a greatest common factor of 2 sine x. So we factor out a 2 sine x, which leaves us with sine x minus 1. Each of those two factors could equal 0. So we split it up into two separate equations, sort of like we did in earlier videos, and we solve each individual equation. first equation, we divide both sides by 2, giving us sine of x equals 0. The sine of x is the y-coordinate. The y-coordinate is equal to 0 twice, at 0 radians and at pi radians. The sine is equal to 0 here at 0 and here at pi. So 0 and pi radians. Okay, then our next one, we would add 1 to each side, which would give us sine of x equals 1. The sine of x is equal to 1 only when pi over 2 is our angle. So that is only one possible solution, pi over 2. Now remember, any of these could be a false positive answer, so we need to check all three. So let's start with 0. If x is equal to 0, our original equation was cosine of 0 equals the sine of 0 minus 1. And that's what we're checking to see if it's true. Well, cosine of 0 is 1, sine of 0 is 0. Well, 1 is not equal to negative 1, so 0 is an extraneous solution. Go on to check pi. Would be cosine of pi equals sine of pi minus 1. The cosine of pi is negative 1, the sine of pi is 0. This one produces a true solution, so pi does work. Finally, check pi over 2. Means that we are doing the cosine of pi over 2 equals the sine of pi over 2 minus 1. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. That also gives us a true solution. So we have two correct solutions to that equation, x equals pi and x equals pi over 2. That does it for the 5.3a notes. Thank you very much for your time and attention.